these recordings are going to be that good. But anyway, all right, so quantum computing. Digital computing is based on gates, and you have a XOR gate and an AND gate, and that's all there are. Everything your processor does is just a combination of XOR and AND, so signals are 0 and 1, and they get combined to make other zeros and ones. And the point of quantum computing is they're also made of fundamental components, but the fundamental components are strange. So it's best to use a Cloud Python environment because I had trouble installing these libraries to simulate a quantum computer outside that. But once you've got it in this thing, you can now synthesize a qubit. And a qubit is a quantum bit. And now if a quantum qubit is in state 0, it's the same as a normal bit in state 0. Every time you measure it, it's going to be 0. So if you make it, you can define the qubit, and then for 10 times you can measure the qubit, and every time you measure it, you're going to get 0. 10 measurements, 10 zeros. So that's just like an ordinary bit. Now qubits, however, can be in between two states. And this is reflected by this thing called the Bloch sphere. So you've got X, Y, and Z, and your qubit can move anywhere on the surface of this ball. And if it's all the way at the bottom, that's the state 1. If it's all the way at the top, that's the state 0. If it's somewhere in between, then it's in a undetermined state called the superposition state, and if you measure it, you'll sometimes get 0 and sometimes get 1. That's how it works. So if you rotate this thing with an X gate, that will rotate it about the X axis, and that will change a 0 to a 1. So before you had zeros, after you do 180 degrees rotate about X, they've all turned into 1s. So you've explored the two certain states, which are the only states normal bits ever have. They're either 0 or 1, they're never anything else. But this is why quantum computers use qubits, and each qubit contains much more information than a bit. It contains all this intermediate states, so it contains basically two floating point numbers for these angles, theta and phi. And those could be high precision. And this is where you reach a real problem. In principle, a quantum qubit is an analog device that stores two floating point analog numbers. The problem is how much precision do you have in those numbers, and the current generation of quantum technology, it is very low. The error rate is very high, insanely high, to where the number of qubits that stay accurate at the end is like 30%. So they waste a lot of hardware and a lot of work trying to improve it. That's the problem with the current generation of quantum computers. They can get these intermediate states, but there's a lot of noise in the circuitry, so you can't really get anything very complicated done with the current generation of hardware. But anyway, now you can reach an uncertain state, you reach a superposition state by rotating about 90 degrees instead of 180 degrees, and then you reach a superposition state, and in a superposition state, when you measure it, you'll get sometimes 0 and sometimes 1. Every time you run it, you'll get a different answer, because when you measure it, it collapses to one of the standard, either 0 or 1. But when you don't measure it, it's a full analog value, and you can modify it and connect it to others, so you can do transformations from one qubit to another. And so instead of having like XOR and NOT, which are the fundamental gates available for digital computing, the gates you have in quantum computers are these like X and Y gates that rotate the thing, and then an entanglement gate. An entanglement is a peculiar quantum property that does not appear in classical mechanics at all. What entangled qubits do is they are connected together. So if whatever state one is in, the other one will now have the same result when you measure it. And the entanglement takes effect even before you measure it. So if I've got one qubit pointing at a funny angle here, and I entangle it with another, that means whenever I measure them later, they will always be the same. And that has an effect on the qubit itself in this uncertain state. And therefore you can do weird kinds of mathematics because the fundamental gates are different. So I had a previous workshop I taught on this. People said, well, if quantum computing can crack, say, RSA encryption with a 2048-bit key, which it can, that would mean it could crack AES with a 256-bit key because that's easier. And it doesn't mean that, because it's not that you have a computer, a general purpose computer, that is much, much faster. What you have is a computer that is fundamentally different. So certain things can be done very well and other things can't be done. So in fact, you can't crack AES. The AES, what happens is It takes 128, 2 to the 128 operations to crack a 128-bit AES key on a digital computer. On a quantum computer, it would take 2 to the 64 operations. It's half as much. So if you move your AES to 256 bits, it's still completely uncrackable forever, even on a quantum computer, even on a perfect quantum computer with no noise, which we are very far from having. So because there is no quantum speed up that's very powerful for AES, but for all public key systems, the speed up is incredible. And that's where you get the, and I don't think I have it in this project, but here's how you draw these things, the qubits that are entangled in the gates. But let me get the Shor's algorithm. This is the reason why quantum computers matter to security people. Even though quantum computers don't really exist yet in any useful way, there is a lot of theory where people have figured out what they would do if we could build them. And there are people selling quantum computers and promoting them, but what they're promoting are really prototypes, not even a beta version yet, that are too noisy to really get much of anything done. But there's huge progress at making them better and better. We all anticipate that in 10 or 20 years, they'll actually get good enough to do this. The Shor's algorithm will show up down here somewhere. There's the diagram. You input the data and you have all these entanglements. And you do this thing called a quantum Fourier transform and put these outputs. And the point of this thing is, it is an analog device. Quantum computers are analog computers, and they are hardware computers. You don't write a program, you build a circuit. Where you put the input, it'll flow through the gates to come to the output. Which, by the way, the same thing's true of a digital computer. That's what the microprocessor is. And so you have to build a certain pattern of these things to do a certain transformation. And it turns out that you can input a composite number here that is the product of two primes, and you can build an algorithm, build a piece of hardware, so with these transformations it gives you an output that gives you one of the prime numbers. It can factor component primes into the primes, and it does it without regard for how long they are, in just a few steps. And this is like, now you've already seen analog computers like this. If you think about a flute, if you just blow over a wedge, you'll just get just a white noise. But if you blow into a flute, the flute carefully has an effect on the vibrations. Some of them enhance and some are canceled out. Now you get a clear note. So the flute is an object which takes input and does a calculation and puts out a certain output. And that's all this is. You built a device which has the physical properties that when you put in data that is the product of two primes, it will cancel out the other factors and give you a product, give you just one of the primes out here. And it doesn't do it by having an algorithm, by guessing them one by one, by looping through anything. It does it by just having the property that the other numbers cancel out and the prime number doesn't cancel out, coming out to the end. So that's what's going to kill all public key encryption systems that we currently have, except for the quantum safe ones that have just been approved, Crystal's, Kyber, and a few others. There's been a contest among cryptographers with the National Institute of Standards for the last 5 years, and they have made some quantum safe algorithms. Anyway, that's quantum computing. Now, a few weeks ago, I had a student that took one of my classes, and he started sending me all these, asking these questions. He said, are quantum computers any use for machine learning? And I said, no, not really. They're not of any value. And he said, you're wrong. And he proved me wrong. So here's what they're good for, which I didn't know. But it turns out to be what I did my PhD thesis on, which caught my attention. I did my PhD thesis on proteins, basically protein folding. And I measured some properties, and I had a model of protein folding, and I modeled the protein as a clothespin. Two boards with one spring between them. Now, protein is 2,000 atoms tangled in a state, and so the particle theorist on my thesis defense committee said, what kind of idiot are you? This is a terrible model. You could have made this model in 1700. Why don't you solve Schrodinger's equation for those 2,000 atoms and get the right model? And they said, we can't do that. We can't remotely get close to doing that. We can't even prove that a heme is a bound state. And a heme is an assemblage of about 12 atoms at the heart of this. And that was true at that time, but that was 40 years ago, I think. Now we can do it. I just realized, if you want to predict the energy state of chemical reactions, you can do it with machine learning and quantum computing together. And that's what happens here. So, consider hydrogen. Dihydrogen, H2, the molecule. If you have two hydrogens and you put them, they naturally fit some distance apart. If you squeeze them closer together, they repel, and that's energy going in like squeezing a spring. If you pull them apart, you have to put in energy, and once you get them far enough apart, they split, and now you have two hydrogen atoms. This energy curve is what describes this chemical bond. And you can predict that energy curve with quantum mechanics and with quantum computing and machine learning together. So you install this thing called PennyLane. PennyLane is the Python library that does this. And so, after you install that thing, you can define this thing called a Hartree-Fock state. And what you're going to do, if you know any physical chemistry, if not, you can just kind of ignore this, but the point is, electrons have orbitals. There's a place the electron can be, and there's an excited state, there's various excited states. But since we're just talking about hydrogen at, say, room temperature, we're not going to have any very highly excited states. So we're just going to find out what's the probability that it's in the ground state, and the probability it's in the first excited state. And so that creates this thing called a Hartree-Fock state. 1,1 means both of them are in the ground state, and they have zero energy in the excited state. That would be the two separate hydrogen atoms not connected. But anyway, that's what this does. This makes that model, and now you can prepare variables to store the energy, and you can define a quantum device that is going to emulate this. And it will show you the diagram of it. And the quantum device has the 4 inputs here, which are the probability that it is in the ground state for the two hydrogens and the probability that it's in the excited state for the two atoms. And then it's going to run them through these calculations that include entangling them together. That's what this diagram is, of the physical wiring of the qubits to do the calculation. And now you can calculate the minimum energy, which also does a machine learning component. And when you're done, you can calculate the energy surface and graph it out, and there it is. You get the energy gets high when they're close together. It falls to a minimum at the right distance, where the natural distance rate, and then here's where you try to dissociate them. So you can now predict the equilibrium bond length, the length where the energy is lowest, and the dissociation energy is the difference in energy between the bound state and the state where you've separated them. That's how much energy it will take to split this molecule apart. And so now you can model a hydrogen exchange reaction where you have an H2, and you're going to, one of the hydrogens are going to escape from this one and fall down there. So it's going to go from H2 plus H to H plus H2. And you can define all that, and you can get the energy curve for that, which is just what you think. This is the barrier you have to go over. And this is the fundamental, simplest chemical reaction. How high is the barrier? Therefore, at any given temperature, what proportion of them are able to climb that barrier and perform this reaction. This is how you predict the rate of reaction as a function of temperature and such. So I thought that was pretty awesome, and it had particular meaning to me because I wrote my thesis on an incredibly primitive attempt to do this 40 years ago when you couldn't do it at all, and I used a horrible model from the 1700s. Now they can predict protein folding with machine learning and get it quite well. I thought I would not live to see that happen. That seemed out of reach. 2,000 atoms in a complicated string in water at room temperature, figuring out what shape it's going to fold into. You can run that in a free Google Colab and get the shape of the proteins now. They can even test drugs in a synthesized Python environment. They can take 100 drugs and they can predict which ones of them are going to work. They found cancer drugs this way. They just take 100 drugs, they run them through a simulator, or maybe 1,000 drugs, they find 10 that look good, and then they try them in patients, and some of them work. So, there's something the animal rights people have been saying forever. You shouldn't be testing things on rabbits and monkeys. You should test them in a computer. And we say, well, we can't do that. The computers aren't good enough. Well, they're getting pretty good. There may come a time when you can actually test drugs in computers instead of testing them on animals. Anyway, so that's one couple of projects that are fun if you want to see that, the quantum computing part. Let me stop.